Okay. Bismillahir Rahmanir Rahim. Well, once again, my name is Dr. Habib Ahmed, and this semester I'm going to, teach the course of the MS course of Modeling and Simulation of Semiconductor Devices, and the PhD course of VLSI Test Principle and Challenges, which is WE724. I gave an introduction in the last lecture about what we are going to cover in this course. Once again, I'm going to give a slight overview of that, and then today we will talk about crystal structures, doping, growth, and about the Silvaco TCAD simulation tool, which actually simulates device processes and also device measurements. Moving on to the next slide. VLSI here stands for Very Large Scale Integrated, in fact, Circuits. There are different abstraction levels of VLSI, which we already discussed in the previous lecture. We have devices. For example, here is an example of a MOSFET in which we have the drain and the source region, which are N-based. So this basically is an N-type MOSFET. And then different devices would combine to form circuits. Could be an inverter. Then different circuits combine to form gates. Could be AND gate, could be NOR gate, etc. Then different gates combine to form modules. For example, adder, subtractor, etc. And different modules combine to form system. Examples of systems are microprocessor and memory devices. Predominantly in this course, we are going to focus on devices. So as I already told you that today would be an introduction into crystal structures, into doping, and some of the other basics. But later, what we are going to study is we are going to cover p-n junction diode, the theory of p-n junction diode, then the theory of Schottky diodes. Later, we are going to study the theory of photodetectors, LEDs, and solar cells. And along with studying the theory, there is a really useful tool. It's called Silvaco TCAD. So in Silvaco TCAD, after covering the theory of each kind of device, for example, when we cover the theory of p-n junction diode, afterwards I'm going to demonstrate the simulation of a diode. We are going to look at its IV characteristics and energy band diagrams and a lot of other parameters in the Silvaco TCAD simulation tool. So the purpose of this course is to enable you to learn the theory of the devices, and then you should be able to simulate those kind of devices in a really simple and straightforward tool, which is called Silvaco TCAD. Keeping that goal in mind, now let us start with the basics, starting from the very basic unit cell concept. So actually, in a crystal lattice, for example, in silicon, we have periodic arrangement of atoms. So just consider this filled circle as a silicon atom, and then we have other atoms placed at a specific distance, which is called the lattice constant of these atoms. And you will see periodic arrangement of these atoms throughout the crystal lattice. Now, a basic building block in this periodic arrangement of the crystal structure is called a unit cell. Like for example, you can assume these 6 number of atoms as a basic building block, as a unit cell. And you can repeat placing this building block throughout the crystal structure, and by the proper repetition of this basic building block of 6 atoms, you can form the entire lattice. Or instead of these 6 atoms, you can pick these 9 atoms shown by this meshed region, and you can assume that this is the unit cell, and just keep repeating this unit cell, and this is also going to lead you towards forming the entire crystal lattice. Now another concept is the primitive unit cell. The primitive unit cell actually is the smallest building block that can be periodically duplicated to result in the crystal lattice. For example, the primitive unit cell would consist of these 4 number of atoms. So the smallest building block which you can repeat periodically in order to achieve the entire crystal lattice. So this is the primitive unit cell, which consists of the smallest number of atomic arrangements which you can periodically repeat to achieve the entire crystal lattice. Moving on to the next slide, we already talked about the primitive unit cell, which is the smallest unit cell. Now, going back to the previous slide, here we are looking at the 2-dimensional periodic arrangement of atoms, while in the next slide over here, we are looking at the 3-dimensional periodic arrangement of atoms. And here we have the primitive unit cell. In 2D, it would consist of 4 number of atoms, but in 3D, you can consider it as a cuboid, where we have 8 atoms, 1, 2, 3, 4, and then 5, 6, 7, 8, forming the primitive unit cell in a 3-dimensional volume space. Now, an important concept over here is the lattice constant, which is the distance between 2 adjacent atoms. For example, imagine we don't have a representation of a filled circle over here, but imagine one atom over here as well, and one atom over here. The distance between these 2 atoms is called the lattice constant. For silicon, this distance is approximately, the crystal structure for silicon is different, but the lattice constant for silicon is approximately 5.42 angstroms. An angstrom basically is 1 into 10 to the power of minus 10 meters. So this distance between silicon atoms is 5.42 into 10 to the power of minus 10 meters. And then we have unit vectors along the x-axis, along the y-axis, and also along the z-axis. So you can represent this cuboid in terms of vectorial representation as well. Now, there are some basic crystal structures. Excuse me. One of them is the simple cubic, the other one is body-centered cubic, and the third one is face-centered cubic. In a simple cubic structure, we have 8 number of atoms. Each atom is located at each corner of the cube. So you can see here is a cube. The cube has 8 corners, and at each corner we have 1 atom, as you can already see. So this is called the simple cubic structure. An example of the simple cubic structure is, for example, phosphorus. Phosphorus has a simple cubic structure. Another kind of structure is called the body-centered cubic. It's similar to the simple cubic structure, but in body-centered cubic, we have an additional atom in the center of the cube over here. Tungsten, by the way, is an example of body-centered cubic structure. Another kind of structure is the face-centered cubic structure. So let me tell you one thing, and then I'm going to ask you a question. So we know that a cube has 8 corners. In a simple cubic, it has 8 corners, then we have an atom at each corner, so it makes it 8 atoms in the simple cubic structure. Body-centered, it has an additional atom in the center of the cube. My question is, how many faces do we have for a cube? Can anybody answer this question?
Six.
We have 6 faces for a cube, right? Exactly. So which means, and then for a face-centered cubic structure, we have an additional atom in the center of each face. So we have 6 additional atoms in a face-centered cubic structure. A gold is an example of a face-centered cubic structure. Moving on to the next slide, there is another kind of structure is the diamond structure, which is constructed by 2 interpenetrating FCC face-centered cubic lattices. Silicon is an example which has a diamond structure. And then we have zinc blende structure which is similar to the diamond structure, but gallium arsenide is an example of zinc blende. In zinc blende, we have alternate gallium and arsenic atoms. Its structure is similar to the diamond structure, but we have alternate gallium and arsenic or other kind of atoms. For compound semiconductor, we have the zinc blende structure. Another kind of structure is called the hexagonal crystal structure, and it's called hexagonal because you can look at the crystal structure from the top, and you can see there are 6 faces. Looking at it from the top, it has 6 faces, so because of that it's called hexagonal crystal structure. Examples of hexagonal crystal structure are gallium nitride, aluminum nitride, indium nitride, and some other materials. One of the key characteristics of hexagonal crystal structure is that it has a tightly packed or closely packed atomic density, and because of that these are kind of robust materials. Now let us talk about the atomic density. Atomic density is the number of atoms for a particular kind of material per centimeter cube. Now assume now instead of this, let us assume, for example, the simple cubic. It's a body-centered cubic structure. Let us go back to the simple cubic structure over here. How many atoms do we have for a simple cubic? As I already told you, there are 8 number of atoms. But if you talk about volume density, now this atom is also shared by another cube in this direction. Similarly, this corner atom is shared by another cube in this direction. Similarly, each corner atom is shared by another cube in different directions. So if you talk about the net number of atoms per this simple cubic structure, it is 8 number of atoms into 1/8, because each atom is shared by different cubes in different directions. So the simple cubic structure actually gives 1 atom per cubic structure. And then if you want to calculate the atomic density, you need to calculate atomic density as the number of atoms per unit cell divided by the volume of the unit cell. For volume, you need to determine the dimensions of the unit cell as well. For example, what is this distance between these 2 atoms? We call it the lattice constant. As an example, let us consider that the lattice constant of this structure is 5.2 into 10 to the power of minus 8 centimeter. So in this case, the volume of this unit cell would be, since it's a cubic structure, and its dimensions are the same, so the volume would be a cube, or the cube of this lattice constant. So this becomes the volume. Now the density would be number of atoms per unit cell divided by the volume of the unit cell. So if we talk about the simple cubic structure, it actually contributes 1 atom per unit cell. So this would be 1 divided by the volume of the unit cell. Now, how many atoms do you think the body-centered cubic contributes per unit cell to this volume? 1 is contributed from all the edges, and then we have an additional atom in the center. So it makes it 2 number of atoms, contribution of 2 number of atoms per unit cell, then divided by the volume of the unit cell. So this way you can calculate the atomic density for a body-centered cubic structure as well. Then going back to the face-centered cubic structure. In face-centered, we already know that the corners would contribute 1 atom per unit cell to the volume density. But how about the faces? How many atoms do we have in total from the faces? 6 number of atoms, because it has 6 faces, right? But then each atom, consider this top face. This is shared by another unit cell towards the top direction, or we can call it the positive z-axis, and another unit cell in the negative z direction, right? So if there are 6 faces, then they are contributing half of the number of atoms towards the unit cell, or 6 atoms divided by into 1/2 becomes contribution of 3 atoms from the faces per unit cell and contribution of 1 atom from the corners of the unit cell. So in total contribution of 4 number of atoms per unit cell, and the density would be 4 number of atoms divided by the volume of the unit cell, and you can easily calculate the atomic density for this as well. Moving on to another important concept, which is the concept of the crystal planes and Miller indices. Now consider this simple cubic structure. The simple cubic structure, and here let's assume this is our positive x-axis, this is our positive y-axis, and this is our positive z-axis. Now consider this grayed area, consider this plane. Does this plane intersect the z-axis? What do you think? Not the z-axis. Does this plane intersect the x-axis? What do you think? So A is actually the x-axis. Do you think this plane intersects the x-axis? Anybody?
Yes, sir.
It intersects the x-axis, right? And how about the y and z-axis?
No, sir.
Does it intercept the y-axis? No, it does not. Does it intercept the z-axis? No, it does not. So the intercept points for this plane would be, for example, 1 for the x-axis, and how about the y and z-axis? What would be the intercept points for y and z-axis? It's well, not exactly 0, because it does not intercept the y and z-axis. So ideally we can say they are going to intercept the y and z-axis at infinity. They never intercept the y and z-axis.
Okay, sir.
Yeah, they never intercept. So so talking about the Miller, let's go to the next slide as well. Miller indices, yeah, so the intercepting points for this would be 1 for the x-axis, and infinity for the y-axis, and also infinity for the z-axis. Now, what are Miller indices? Miller indices are actually the reciprocal of the intercepting points for these planes. So let us calculate the reciprocal of each of these points one by one. The reciprocal for the x-axis would be 1/1, which comes out to be 1. How about the reciprocal for the y and z-axis? The intercepting point is infinity, so 1/infinity becomes
0.
0 for the y-axis and 0 for the z-axis. So the Miller points actually determine the crystal plane. For example, this plane you can represent it using parentheses, and you can call it 1, 0, 0 plane. Let's move to another example. You can see this grayed out plane in this simple cubic structure once again. So as you can see over here, this plane intercepts the x-axis, and it also intercepts
Y-axis.
the y-axis, but it does not intercept the z-axis. So the intercepting points for this would be 1, 1, and infinity. And how about the reciprocals? What are the reciprocals for this? 1/1 is 1, then once again 1/1
0.
1, 1, 0. 1, 1, 0 are actually the Miller indices. Miller indices are the reciprocal of the intercepting points. So this kind of plane can be represented by 1, 1, 0. Consider another example. Here we have a plane which is intercepting the x-axis, the y-axis, and also the z-axis. So in this case, the intercepting points are 1, 1, 1, and their reciprocals would also be 1, 1, 1. So the Miller indices would be 1, 1, 1, and this kind of plane is, you can call it the 1, 1, 1 plane. Now, okay, we calculated the Miller indices. What is the significance of Miller indices? For example, you might like to grow aluminum nitride or gallium nitride on top of silicon, and the lattice constant, this distance between atoms, is different for aluminum nitride or for gallium nitride as compared to silicon. So you can perform the growth of gallium nitride or any other kind of material on silicon in different plane directions, 1, 0, 0 or 1, 1, 0 or 1, 1, 1. And one of these planes would give you the best results in terms of growth of materials on top of a substrate. So that is the significance of Miller indices in crystal planes. It's really important. Like even growing the basic p-n junction diode requires a lot of paying a lot of attention towards the crystal planes and then towards the growth, so that you can achieve highly crystalline devices in order to achieve optimal performance from your devices. Moving on to the next slide, let us try to calculate the Miller indices for this example. Now, in this example, don't get confused with the x-axis, y-axis, and z-axis. These are just conventions. But in this example, we assume that this is our x-axis, this is our positive y-axis, and this is our positive z-axis. So what are the intercepting points? 4, minus 3 for the y-axis, and 2 for the z-axis. And these are the intercepting points, 4, minus 3, comma 2. And we want to calculate the Miller indices, or we want to represent this in terms of a plane. So invert the value, find out the reciprocals towards calculating the Miller indices. This becomes 1 over 4, comma, minus 1 over 3, comma, 1 over 2. One of the rules of Miller indices is that you should represent Miller indices in whole numbers. You cannot represent them in fractions. So in order to convert them into whole numbers, you multiply them with their least common multiple, which is 12 over here. So multiply it with 12, you get 12 into 1 over 4 is 3, 12 into minus 1 over 3 is minus 4, and 12 into 1 over 2 becomes 6. So now 3, minus 4, and 6 is these are your Miller indices and also your crystal plane. But it can also be represented in this form. Minus 4 can be represented with a 4 over bar. So the crystal plane over here is 3, 4 over bar, 6. Another concept that I want to talk about is crystalline defects, impurities, and different kind of dopings in semiconductors. We already talked about periodic arrangement of atoms in a crystal lattice without any defect, without any kind of defect or impurities. But defects could be present in semiconductors, and these could be point defects, which are of the order of an atom, vacancies, interstitials, impurity atoms. There could be line defects, for example, dislocations, planar defects, stacking faults, etc., and volume defects, precipitates, and voids. And now let us talk about each kind of defects. So over here, for example, we have periodic arrangement of atoms. We have this one atom, and then these atoms are equally spaced from each other. The felt circles are representation of periodic arrangement of atoms, periodic order of atoms in the crystal lattice. But look over here. If there is a missing atom in this part, then you say there is a defect in this kind of semiconductor. A missing atom is called vacancy in a semiconductor. And there is also possibility that if all these atoms are silicon atoms, if at this point this silicon atom is replaced with another atom, for example, it could be phosphorus or it could be boron, then we call it substitutional impurity. Another kind of impurity is called interstitial, in which you still have this periodic arrangement of atoms, but there is another atom which sits like right in the middle of these ordered periodic arrangement of atoms. So an additional atom in the middle of the periodic arrangement of this crystal lattice is called interstitial impurity. And there is also always a possibility of this. If the size of this atom is smaller as compared to the size of the individual of the original atoms in the crystal lattice, the smaller atom has a chance to sit down in the middle of somewhere in the crystal lattice, and it's going to distort the crystal planes for the crystal structure. Another kind of defects are called line defects. In the previous, here is a two-dimensional representation of the crystal lattice. Here we have a kind of a three-dimensional representation of the crystal lattice. So we have lines, for example, we have these vertical lines extending from the bottom towards the top, and what happens is you often see it in terms of growth when you are growing different materials, silicon, gallium nitride, aluminum nitride. If the growth has started, if this is the starting point of the growth, then you start depositing more number of atoms over here, then you start depositing more number of atoms over here. So up to this point you see a pattern. You see lines, periodic arrangement of lines in the vertical direction and also in the horizontal direction. But after arriving at this point, we see that now an additional line of atoms has introduced in the middle of the crystal structure. And this kind of additional line is called edge dislocation. It's a kind of a line defect. There could be planar defects as well. For example, grain boundaries are type of planar defects. Grain boundaries are actually found in polycrystalline material. If the entire crystal has one kind of periodic arrangement of atoms, we call it monocrystalline. But if we see that over here there are regions where we have periodic arrangement of atoms, individual regions over here, but these individual regions are not synchronized with the other regions, and their boundaries are called grain boundaries, because these atoms terminated over here have dangling bonds, and we call them impurities because these dangling bonds introduce a lot of current flowing across the grain boundaries, which kind of deteriorates the performance. For if you are using it in diodes, it's going to deteriorate the performance of the diodes. It's not going to give you a perfectly exponential rise kind of voltage versus current versus voltage curve. So these grain boundaries deteriorate the performance of devices. Another kind of defects are called volume defects. For example, you might like to grow a perfect crystal, but as an example, if you are doping gallium nitride with magnesium, then there is a possibility that instead of magnesium to be uniformly distributed in the crystal lattice, it might start accumulate somewhere over here and form precipitates, which is one kind of volume defect. There could be voids inside the crystal lattice as well. Moving on to the next concept, which is bonding, model, and dopants. And consider the example of silicon. How many electrons do we have in the outermost shell of silicon? Before that, what is the atomic number of silicon? You can Google it, right, if you don't know. The atomic number of silicon is 14. 14, right? Which means it has 2 electrons in the first shell, 8 electrons in the second shell, and 4 electrons in the outermost shell, or the valence shell. And these 4 electrons are available for bonding. So consider this is a silicon atom, and these 4 are the 4 valence electrons of the silicon. This silicon atom starts bonding with other silicon atom. So over here it shares electrons with another silicon atom. Similarly, it keeps sharing electrons with other silicon atoms in all directions, and now the bonding requirement for these silicon atoms is fulfilled, because each of these silicon atoms have now, by sharing of electrons with its neighboring silicon atoms, each of them has 8 number of electrons in their outermost shell. So how do you represent them in terms of the band gap? For that case, in band occupation at low temperature, which is 0 Kelvin, at 0 Kelvin, all these electrons are attached to the valence shell of the silicon atoms, which means that the valence band is fully occupied by electrons and the conduction band is totally empty of electrons. And an analogy of this is that an analogy of the valence band is fully occupied by electrons is that if you have a jar full of marbles and you try to shake it, but they are tightly packed, there is no room for the marbles to move around inside the jar. So similarly, at 0 Kelvin, if you don't have holes in the valence band, there is not going to be any space for the electrons to move around, and the current flow in this case would be 0. And an analogy at 0 Kelvin for the conduction band over here is that we don't have any electrons in the conduction band. An analogy for this is, once again, you have another jar which is empty of marbles. If it is empty of marbles, it doesn't have any marbles, which means the marbles cannot move around because we don't have any marbles, so current is not going to flow. And the band gap, do you know what is the band gap for silicon? Any idea?
No, sir.
The band gap, it's an important number and you will have to deal with it time and time again, so try to note it down. Because we are going to study devices, PN junction diodes, Schottky diodes, LEDs, solar cells, and photodetectors. So we will talk about band gaps of different materials, especially silicon is the basic example. The band gap of silicon is 1.1 electron volts, which is the difference between conduction band and valence band for silicon. And that actually means that if you want to move an electron from the valence band to the conduction band for silicon, you need to provide an energy of 1.1 electron volts. It could be thermal energy or it could be light energy. But if you want to move an electron from the valence band to the conduction band, you need to apply that amount of energy. So now the point is, here we are talking about 0 Kelvin, but what happens if we increase the temperature? If we increase the temperature, which means that we are providing some sort of thermal energy to this structure, right? So if we increase the temperature, what happens in the crystal lattice is that some of the bonds would get broken. Like for example, here you can see that electron has detached from the outermost shell of one of the silicon atoms. It has broken its bond and now it can freely move around inside the crystal lattice. And in terms of band gap, you can see that now an electron has jumped from the valence band to the conduction band, leaving behind a hole. What is a hole? A hole is just an absence of electron, is called a hole. So even over here, now we have a missing bond over here, but it provided us an electron which can freely move around inside the crystal lattice. And then if we apply voltage to the structure, the electron would flow in a particular direction. Right now, if no voltage is applied, it's going to move around, but randomly. But if we apply a voltage, we give direction, we give an electric field, the electron is going to flow in a particular direction in that case. As I already told you, if you apply a voltage, we have this electron, this broken bond, and this electron then moving on to the next slide, and you can represent it with this example. So applying a positive potential means towards the left means this is going to attract the electron in this direction, and the negative potential would attract the hole towards the right. So looking into the next slide, now the electron has moved slightly towards the left, and the hole actually moves towards the right, which also means that actually an electron jumps from this location to over here, fulfilling the bond requirement over here, but leaving behind a hole in this arrangement. In this, the electron would further keep moving towards the left, and the hole would further keep moving towards the right. Similarly, going back to slide number 22, you can see that the electron would move towards the left, and the hole would move towards the right. You can see the movement of electron in this slide number 23. Then moving on to slide number 24, you can see the movement of electron and hole in this slide as well. Material classification based on the size of the band gap. So based on the size of the band gap, we can classify materials into metals, semiconductors, and insulators. But before talking about material classification, I want to talk about another concept, which is intrinsic carrier concentration. Let's go back to slide number 21. Not 21, slide number 21. As I already told you that if we increase the temperature above 0 Kelvin, some of the bond get broken and electron jump from the valence band to the conduction band. And this is an example of just one electron, but actually if you increase the temperature, a lot of other electrons would move from the valence band to the conduction band, and we would have a certain carrier concentration in this material. If this material is silicon at room temperature, so once again it's another important number that you need to memorize to remember. The intrinsic carrier concentration, or the carrier concentration for silicon at room temperature, is 1 into 10 to the power of 10 per centimeter cube. So at room temperature, 1 into 10 to the power of 10 number of electrons gain enough kinetic energy, enough energy to transition from the valence band to the conduction band. Intrinsic carrier concentration is represented by Ni, and it's once again 1.5 10 to the power of 10 for silicon. The intrinsic carrier concentration depends on two parameters. Temperature, if you increase the temperature, the intrinsic carrier concentration also increases. And it's dependent on the band gap of the semiconductor material as well. If you increase the band gap, the intrinsic carrier concentration would be reduced. For example, as I already told you, it's 1 into 10 to the power of 10 per centimeter cube for silicon. And silicon has a band gap of 1.1 electron volts. And these are important numbers for you to remember, because you will have to deal with a lot of numericals based on these values. The band gap of germanium is 0.66 electron volts. And the intrinsic carrier concentration for germanium is 2 into 10 to the power of 13 per centimeter cube. If you increase the band gap to 1.42 for gallium arsenide, the intrinsic carrier concentration has reduced to 2 into 10 to the power of 6 per centimeter cube. And then for gallium nitride, the intrinsic carrier concentration is 1 into 10 to the power of 14, minus 14 in fact, per centimeter cube, because its band gap is even wider. So based on the band gap of semiconductors, we can classify materials into metals, semiconductors, or insulators. In case of metals, the conduction band and the valence band overlap each other. So we always have a lot of carriers available for conduction. We don't have any problem of carrier unavailability for conduction. So metals can easily conduct because their conduction band and valence band overlap with each other. In case of semiconductor, there is a gap between valence band and conduction band, which is 0.66 electron volts for germanium, 1.12 electron volts for silicon, and 1.42 electron volts for gallium arsenide. And based on the band gap, their carrier concentration ranges between 10 to the power of 6 to 10 to the power of 14 per centimeter cube for these materials. If you further increase the band gap to 5 electron volts for diamond or to 8 electron volts for silicon dioxide, now the number of the intrinsic carrier concentration would be approximately 0, which means no electrons jump from the valence band to the conduction band at room temperature for silicon dioxide or diamond. And because of its poor conduction, we call this kind of material as insulator. Doping of semiconductors. Let me see how many slides do we have in 27 onwards. All right, we have a few slides. Okay. Since I'm recording this lecture, so let's have a break of approximately 10 minutes so that I can save this video, and then we will resume at 5:25. I think we have like 30 minutes of lecture left for the rest of the day. So, all right, see you around at 5:25 so that I can save the video lecture so far. All right.
Okay, sir.